Next, our topic for today is matrices. So we are solving matrices, right? So we'll start with our first video, that's Mark 1. We'll start with Mark 1. Right. So we are using the Aquila in the routine chapters 27. Right. So the first page, a matrix. So the idea of a matrix is a rectangular array of numbers, usually encased in parentheses. Right. So we just have a rectangular array of numbers. A rectangular array of numbers, usually in parentheses, and that's an array. Oh wow, why is my understanding not showing? Good. A rectangular array of numbers, so A, B, C. I'm using A, B, C, D, F to represent the numbers. So this is a matrix. Right. Mostly, sometimes also it can be a square, like A, B, C, D. Numbers in a parenthesis, that's a matrix. And then sometimes to just A and B, it's also a matrix. Right. So let's see this example. In this example, this matrix, this table was reduced to this matrix by just taking each one, then putting them here, taking each one and putting them here, and that's simple for this one. Let's see the definition of a matrix. We are here. A matrix is a rectangular array of numbers. The numbers in the matrix are called elements, right? So we just have a rectangular array of numbers. Array of numbers, right? And then the numbers in there are called elements. So when we come up here, A, B, C, D, E, F, they are the elements. The order of a matrix is the number of rows times the number of columns. So it means that what order of matrix means is the number of rows times the number of columns, right? RC. You can use remote control to remember that. So for this matrix, how many rows are here? We have this row, and then we have this row. So that is 2 by, and then how many columns? We have 1, 2, 3 by 3. So in all, we have, this is a 2 by 3 matrix. Let's try this one too. We have 2 rows, 1, 2. So say 2 by 1, 2. A 2 by 2 matrix. Perfect. This one is a 2 by 1 matrix. Perfect. So in this example, they gave example in this on the book. In the book, they give examples here. Then note also that a matrix in printings, in a printing, it will be denoted by a capital B, right? A bold B. Then the element will be shown. Perfect. I think we are good with all this, right? And then note this one. Note this. Comments are not used in matrices. Gaps are not left between the columns, right? So we just leave gaps here. Gaps are left. We don't instead of 1, 2, 3, right? It's like this, 4, 5, 6. We don't do this. We rather leave spaces. Right. So if I want to write 12, I'll put it together and then leave 2. Then we make the spaces evident that yes, there are different numbers. Let's move on to types of matrices. The types of matrices, we have column or row matrix. A column or row matrix has only one column of elements. So this is an example. A column matrix has only one column. So this matrix AB is called a column matrix because it's made of only one column. Right. Sorry for my wrong spelling of column. Yeah, perfect. I get it now. Right. So this is a 2 by 1 matrix, and because 1 represents a number of columns, it's a column matrix. What of a row matrix? The same way, a row matrix will have only one row. So a matrix like these are row matrices because it's just one row but two columns. So the order of these matrices will be 1 by 2 because one row by two matrix and two columns. These are the types of matrix. Let's move on. We have also the null or zero matrix. A null or zero matrix is a square matrix in which every element is zero. So whenever we have a square matrix, right, so let's see the keywords here. A square matrix, every element is zero. So these are the keywords. The first keyword here says a square matrix. We know what a square matrix is. So a square has all sides being equal. In that same way, a square matrix will have all same rows and columns. So if it is a 2 by 2, it is square. If it's a 3 by 3, it's a square matrix. If it's a 4 by 4, it is. If it is a 2 by 3, it fails to be a square matrix because they are not the same. So it becomes a rectangular matrix, right? And then 3 by 2, it fails to be a square, it becomes a rectangular matrix. Perfect. So whenever we have a square matrix and every element is zero, then that is the null or the zero matrix. So the zero matrix typically looks like this, right? For 2 by 2 and then 3 by 3, it will look like this. So it's just matrices with zero in all the element spaces. The zero matrix is the identity matrix for addition, right? We know what identity means. It's acting as a mirror. What this means is, we'll get there, but I can give you a brief understanding of what this statement means. What this means is, when we are adding a matrix, we are adding matrices. Whenever we add this matrix, which is our null matrix, it wouldn't cause any change to what we added. So in normal algebra, we will say 0 is our identity in addition, because if I add 0 to 4, I also get 4. That means 0 didn't have any effect. We get the same. If this is our object, this is our image, our object always remains the same as our image, which means that this 0 is an identity element, right, in the addition, right, in this addition process. In the same way, multiplication has 1 as the identity element, because whenever you multiply a number by 1, you get the same number. So we say this 1 is an identity element. So identity elements mostly act as mirrors. That's an analogy you can keep in your mind, as mirrors in an operation, right? So whatever operation they are found in, when you operate them, they don't cause any change. They produce the same answer as what we had originally. So when we add this, which is the null element, any of these to any matrix, it wouldn't change the matrix. We have the same thing. Note that a zero matrix may or may not be a square matrix. Okay, then why did they say? Okay, so a zero matrix can be a square matrix. It can also be not a square matrix. So it means that there are possibilities of it being 3 by 2 or a 2 by 3 or any other form of matrix, even if it's not square. Perfect. Let's go look at rectangular matrix. A matrix in which the number of rows is not equal to the number of columns, right? Number of rows is not equal to the number of columns. It's called a rectangular matrix. We've seen this already. Because the number of rows this one is a 1 2 2 by 3 matrix. This is the number of rows, this is the number of columns. Because the number of rows is not equal to the number of columns, we say this is a rectangular matrix. Then you really see it looks like a rectangle, right? A rectangular matrix, so that's a simpler way to see them. They look like a rectangle. And then square matrices has the same number of rows and columns, so 2 by 2, 3 by 3, 4 by 4, and then you see they look like squares. Unlike here, they look like rectangles, right? Let's look at the next one, unit matrix or identity matrix. So a square matrix having every non-diagonal element equal to 0 and every diagonal element equal to 1 is called a unit or an identity matrix, right? So let's see the keyword in here. We have every non-diagonal element, right? This is 0 and every diagonal element is 1. It's called the unit or identity matrix. So first, let's see non-diagonal elements. What do we mean by diagonal or non-diagonal elements? So when we take a matrix, we call this the leading diagonal of the matrix, right? So every matrix has a diagonal. The diagonal is the so it's an imaginary line that moves from the top to the extreme left diagonally, right? Extreme right diagonally. So these elements that are along the diagonal, those are the diagonal elements. So when we want to get a unit matrix, or we want to know whether a matrix is a unit matrix, it will have zeros everywhere except the leading or the diagonal element. So an example will be for a 2 by 2 will be just this, then zeros everywhere. For 3 by 3 to be 1 1 1, then zeros everywhere. So this is the identity or unit matrix. For 4 by 4, let's guess to be 1 0 0 0 0 1 0 0 0 0 1 0, then 0 0 0 1. This how to be. We always make sure there are ones on the diagonal and then zeros elsewhere. That is it for unit matrix. So these are the unit matrix, just as we said. Note that a unit matrix is always diagonal matrix. So a unit matrix is always a diagonal matrix. A diagonal matrix is a matrix that has elements on only the diagonal. Elsewhere, there are zeros. Okay, that is a diagonal matrix. So it has only numbers on only the diagonal. Elsewhere, any other element apart from the ones on the diagonal, those ones are zero. Then we term that matrix as a diagonal matrix. So these are examples of diagonal matrix. You see here we have 1 and 3 here. Elsewhere we have 0. We have 1 5 9. Any other elements apart from the leading diagonal are 0. So this is a diagonal element, diagonal matrix. Here too, oh sorry, we have elements here, elsewhere it's 0. So this is a diagonal matrix. And then we have equal matrices. So two matrices are said to be equal if the elements they have correspond at the same entries, right? So if their corresponding entries are the same, so let's see, corresponding entries are the same. Let's see, what do we mean by corresponding entries? How are you going to get the corresponding entries? So when we compare matrices, entries that are at the same position are said to be corresponding, right? Are said to be corresponding. So if I have A, B, C, D corresponding or equal to E, F, G, H, then elements that are in the same position are corresponding, they are equal, right? A is equal to E, C is equal to G, D is equal to H, and then B is equal to F. For these two matrices, so let's say this is matrix A and this is matrix B. For A to be equal to B, right? For A to be equal to B, for this to be true, right? A should be equal to E, B should be equal to F, C should be equal to G, and then D should be equal to H. That means that if you have elements, a matrix like 1, 3, 4, 5, we can say that it is not equal to 1, 5, 4, 3. Right? They are not equal. But if I have another one that is 1, 3, 4, 5, that's 1 here, 1 here, 3 here, 3 here, 4 here, 4 here, 5 here, 5 here, then we can say these elements are equal, right? So we'll end here and then continue on the next one to addition of matrices in Mark 2. Addition of matrices in Mark 2.